Okay, so welcome everyone to another differential geometry seminar here. Today we have the pleasure of receiving the talk by Nicoletta Tardini from Università di Parma, who is going to talk about complex symplectic manifolds, cohomology, and deformations. Thank you very much, Nicoletta.
Thank you very much for the introduction, and of course, thank you very much for the invitation to give this talk. So I will present some results that I obtained in collaboration with Giovanni Bazzoni, Marco Freibert, and Adela Latorre about this special class of geometric structures on smooth manifolds that are complex symplectic structures. Sometimes they are also called holomorphic symplectic structures. And in fact, I will focus mainly on their cohomological behavior, and then I will say what we know about their behavior under small deformations, okay? So the plan of the talk is the following. So first of all, I will recall the definition of complex symplectic structures, and we will see we will see some equivalent definitions of complex symplectic structures, in fact, and we will see some properties and some examples, and then I will focus on their cohomological properties, okay? Because in fact, the existence of a complex symplectic structure and a complex manifold will give some cohomological obstructions and in fact also some topological obstructions. And then for, let's say, the main part of the talk essentially will be devoted to discuss their behavior under small deformations, okay? All right, so, okay, so let me start. So just for notation, I will use the letter M to denote a smooth manifold. Most of the time, this manifold will be compact. So in case I forget to say that, I will assume most of the time that M is compact. And let me recall that a complex structure on a smooth manifold that I will denote with J is a 1-1 tensor that squares to minus the identity. So this means that, in fact, we have just an almost complex structure. But now I will assume during the talk that, in fact, this structure is actually integrable, which means that this condition is satisfied. So the Nihe-Noyes bracket is, the Nihe-Noyes tensor, sorry, is vanishing, okay? So these two conditions, the fact that we have this tensor that squares to minus the identity plus this integrability condition, means that we have a complex structure. So in fact, we have local holomorphic coordinates and so on. Okay, so now, in fact, of course, J is defined in this way on vector fields, but then you can extend the action of J on one forms, for instance, in this way. And so if you extend J to the complexified space, what you have is a decomposition of the space of complex valued one forms on M into two spaces, one that we call 1, 0, the space of 1, 0 forms, and the space of 0, 1 forms, where here J is acting as multiplication by I, and here J is acting with multiplication by minus I, okay? So we have this decomposition that then can be induced in any degree this way. So what you have is that on a complex manifold, if you take the space of complex valued differential forms of, let's say, degree k, then we have a decomposition, right, of the into the spaces of PQ forms, okay, where here P plus Q is equal K, okay, gives the total degree, okay? So we have a natural bigrading on the space of forms that is induced by the complex structure, okay? So you change the complex structure and this bigrading is changing, okay? And according to this decomposition, also the exterior derivative splits. In fact, if you take the extension of the exterior derivative to complex value differential forms, and that we call again D, and then you act, for instance, on a PQ form, then you obtain a form. So the differential of this form will be a form that is the sum of piece that has B degree P plus 1 Q and another piece that has B degree P Q plus 1. And this, again, in fact, is equivalent to the integrability of the complex structure. So, in fact, the differential D is splitting as a sum of two differential operators, del and del bar. So del is the 1,0 component of D, so it's the projection of D on this space, and the bar is the conjugate, okay? So it's the projection of D on this space. And so what happens is that since D squares to 0, also these two differential operators square to 0, and they anti-commute. Okay, and okay, so now let me recall this definition, that is the main definition for my talk. So a complex symplectic structure, sometimes called also holomorphic symplectic structure, is a pair given by a complex structure, J, and then we have this form, omega C, that is D-closed and non-degenerate, and it has B degree to 0 with respect to the complex structure J, okay? So we have an holomorphic 2 form that is D-closed and non-degenerate. And we will call this omega C the complex symplectic form, and we will talk about complex symplectic manifolds, okay? So this is the main definition. And clearly, immediately you can see that, in fact, this type of structures can exist only on manifolds of real dimension 4n. And the canonical bundle of the complex manifold becomes immediately holomorphically trivial. Okay, so this Km is the canonical bundle, so it's a bundle of 2n 0 forms, if the real dimension is 4n, and it is trivialized globally and holomorphically by using this omega C, because you take omega C to the top power n, and this is nowhere 0, so and it's closed. So this means that immediately you see that these structures cannot exist on any complex manifold, okay? And in fact, the previous definition was a sort of, let's say, what you have here, you have really, not really a real symplectic structure, right? This is complex symplectic because it's a 2-0 form, right? But in fact, you can define complex symplectic structures in an equivalent way where real symplectic structures appear. So this result was proven by Bazzoni, Freibert, Latorre, and Menke. So they proved that you can think of complex symplectic structures in this way. So as a pair, you have J that is the complex structure, okay? And then what you have is a real symplectic form. So omega is a real symplectic form now, such that omega and J are related by this condition. So essentially, J is symmetric with respect to omega. Okay, so you have this nice compatibility relation between omega and J. And let's say the bijection between these two definitions is as follows. So if you take a complex symplectic structure as in the first definition, so omega C was a 2-0 form that is closed and non-degenerate, then the real symplectic form in this definition is just the real part of omega C. Okay, so you take the real part of omega C, and the inverse is given in this way. So you take omega as a symplectic form that is compatible with J through this relation, and then you can define omega C in this way, and you can check that this is a 2-0 form that is closed and non-degenerate, okay? So you can think of complex symplectic structures in these two ways. And also, I would like to point out this results of Verbitsky, essentially, that essentially it's saying that the complex structure J is uniquely determined by the complex symplectic form, omega C. Because this happens. So Verbitsky gave this definition for a real smooth manifold, okay? So now I'm not fixing a complex structure, okay? So I have a 4n dimensional smooth manifold. And a two-form, a complex value, the two-form on the manifold, is called C-symplectic. This C probably stays for complex, essentially. So this was the definition of Verbitsky. So this omega is called C-symplectic if omega is closed. Omega n to the power n plus 1 is 0, and the wedge product of omega n with omega bar n is pointwise non-vanishing. Okay, so we have these three conditions. And clearly, if you take a complex symplectic form, it satisfies these three conditions. Okay, so it is C-symplectic. But the point is that if I have a real manifold with a C-symplectic structure, we can construct a compatible complex structure as follows. So the idea of Verbitsky is the following. You can take, you can define this bundle. I mean, you can show that it is a bundle. It is well defined. If you take the kernel of omega, so we call T01 of omega the kernel of omega. I mean the vectors, complex vectors, such that the contraction of omega with V is equal to 0. And we call these vectors 0, 1 vectors, okay? And then you define T10 as its conjugate, okay? And then these two conditions, the second one and the third one, ensures that this is, let's say, well-defined, and they are in direct sum, and their sum is equal to the complexified tangent bundle. Okay, so this follows from the second condition and the third condition. So now you probably see where I'm going, because now, essentially, we are defining an almost complex structure because actually, we are defining more. We are defining a complex structure because it turns out that if you assume that omega is closed, just like here in the first condition in this definition, then T01 is closed under Lie bracket. So what I'm saying is that if you take the Lie bracket of two 0, 1 vectors, so which are essentially in the kernel of omega, so the Lie bracket is still in the kernel of omega, so it's still a 0, 1 vector. And this follows using the fact that the differential of omega is 0. I mean, it's easy to check. It's just you take the formula for the differential D acting on a 2 form, and then you use that to show that this T01 is closed under Lie bracket. Okay, so now essentially we have defined a complex structure because you define J as minus I on 0, 1 vectors and I on 1, 0 vectors. And this almost complex structure is in fact an integrable complex structure because of this condition, okay? The fact that T01 is closed under Lie bracket is an equivalent condition to integrability, okay? So this is defining an almost complex structure, and by definition of T01, that was the kernel of omega, it turns out that the form omega is of B degree 2, 0 with respect to this complex structure. So essentially, we have constructed a complex symplectic structure. So really, I mean, J is uniquely determined by omega in this sense, okay? Okay, so now that we saw the definition, so let me present a few examples, I mean, the classical ones. Then, I mean, going on with the talk, we will see several other examples. But let me start with the first one that usually people have in mind of complex symplectic manifolds, and they are hyperkähler manifolds, right? So a hyperkähler manifold is defined as follows. So we have a smooth manifold M, and that is endowed with three complex structures, I, J, and K. And these structures behave like the quaternionic units, okay? So I and J anticommute, and K is defined as the composition of I and J, okay? So this means that we have an hypercomplex manifold. Then, in fact, every hypercomplex manifold admits an hyperhermitian metric, which means that we have a Riemannian metric. So G is just a Riemannian metric that is Hermitian with respect to I, J, and K. So here, L stands either for I or J or K, okay? So we are saying that, for instance, I don't know, take I, so G of Ix, Iy is equal to Gxy for any xy vector fields, okay? So this means that G is Hermitian with respect to these three complex structures. And every time we have Hermitian metric, we can define the fundamental form that is a two form on the manifold that is defined in this way. So again, think of L as one of these three structures. So omega L of xy is defined as G of Lxy. So this is a real positive 1-1 form. It's the fundamental form of the Hermitian structure. And by definition, hyperkähler means that these omega L for I, J, and K, they are closed. So they are symplectic forms, essentially compatible with the complex structures I, J, and K. So this means that we have an hyperkähler manifold. And hyperkähler manifolds are not, I mean, we don't have many hyperkähler manifolds, in fact, but they are for sure complex symplectic, because if you define omega C, I mean, this 1/2 is not important. So take omega C as omega J plus I omega K, okay, using this definition. So omega J is the Kähler form for the complex structure J, and omega K is the Kähler form for the complex structure K. So, and you take this sum. This is, of course, it's a two form because it's the sum of two forms, but it is of B degree 2, 0 with respect to the complex structure I. And it is clearly closed because they are closed, and it is non-degenerate. Okay, so this I omega C is in fact a complex symplectic structure. Okay, and in fact, what we have, it's a sort of converse. I mean, that if this was proved by Beauville, that if we have a compact Kähler manifold that admits a complex symplectic structure, then it has to be, in fact, hyperkähler. It has to be of this type, okay? So if we have a compact complex manifold with a Kähler metric that admits also a complex symplectic structure, then it has to be hyperkähler. Okay, but we have also known Kähler examples, of course, okay? In dimension 4, real dimension 4, compact complex surfaces admitting complex symplectic structure are completely classified. In dimension 4, you can just have K3 surfaces or tori, so they are Kähler, or the only known Kähler example you have is given by the primary Kodaira surfaces, okay? These are in manifolds. We would talk about, we will see some explicit examples later in higher dimensions, so I will not really want to present the construction on the primary Kodaira surface, but and these are the only possible examples, okay, in dimension 4. And then other examples are provided by nil manifolds. So nil manifolds are quotients of simply connected nilpotently groups. Let's say G by a lattice gamma. So this gamma is a co-compact discrete subgroup of G, and these manifolds are called nil manifolds. And there are some examples, of nil manifolds admitting complex symplectic structures. I think the first examples, some of the first examples I saw were constructed by Yamada, and then some years ago, Bazzoni, Freibert, Latorre, and Menke studied deeply the existence of complex symplectic structures on nil manifolds in case the complex structure is invariant, which means that essentially comes from a complex structure on the associated Lie algebra G of the Lie group G. And so they studied complex symplectic nilpotent Lie algebras. And they showed that if there is this condition on the center of the Lie algebra, then in fact they can always, these examples can always be obtained from lower dimensional examples. Okay, so in fact, this allows them to construct examples, many examples in any dimension. Okay, and this for nil manifolds. So nil manifolds are that admit complex symplectic structures are, let's say, well understood. And other examples are provided by Sol manifolds, where here I'm not assuming that G is important, but more in general, G can be solvable. Okay, so the quotient is by simply connected, solvably grouped by a lattice. Okay, and some explicit examples were constructed by Antas, Cattaneo, Rolensky, Tomassini. And a few years ago, we studied the existence of complex symplectic structures with Bazzoni, Freibert, and Latorre on almost a billion Sol manifolds. Okay, so almost a billion Sol manifolds means that the Lie group G is almost a billion. So there exists a codimension one, a billion ideal. And in this case, you can, in fact, explicitly characterize the existence of complex symplectic structures, let's say, by saying how the adjoint operator acts on this almost abelian group. And so, again, we were able to construct examples in any dimension, compact examples. You can really, let's say, write them explicitly, okay? So there are many examples. This was just to say that we have many examples of complex symplectic manifolds in any dimension, but all these non-Kähler examples, because nil manifolds are non-Kähler unless they are tori, and also for some manifolds the Kähler condition is well understood, but all these examples are not simply connected. And so in fact, I should point out probably that the only examples of compact simply connected non-Kähler complex symplectic manifolds are due to Guan. Okay, so these are the only examples that are known that are simply connected, but probably these examples are not very explicit. Okay. They're not like, I mean, interesting enough, they start from nil manifolds. The construction of Guan starts from nil manifolds, but then the examples are not easy, okay, to construct. And they are the only one, as far as I know, that are simply connected. Okay, so and this somehow is because we don't have general techniques to understand whether, I don't know, a complex manifold admit a complex symplectic structure. So with Bazzoni, Freibert, Latorre, we first wanted to understand, for instance, if we have some cohomological obstructions to their existence. And so let me first recall some definitions, okay? So in complex geometry, if you have a complex manifold, you can define several cohomology groups. Using the operators we saw before, the operators del and del bar, they were differential operators, right? And so they square to zero and anti-commute. So you can define the Dolbeault cohomology. In this way, you take the operator d bar that squares to zero, and so you quotient d bar closed forms over d bar exact forms. Well, PQ forms. I'm talking about PQ forms because all these cohomology groups are bigraded, okay? So they have the B degree coming from the complex structure, right? And this is the Dolbeault cohomology. But then we can also define the Bochern cohomology using PQ forms that are both del closed and del bar closed, and you quotient by the d bar exact forms. And dually, for apli cohomology, you take d bar closed forms over the sum of del exact forms plus the del bar exact form. And so all these cohomology groups are holomorphic invariants, and they are very helpful if you want to study complex manifolds. And if your manifold is compact, they are finite dimensional. I mean, there is a whole Hodge theory behind these cohomology groups, and it turns out that these cohomology groups, if the manifold is compact, are finite dimensionals, okay? And so we proved that if you have a compact, again, I'm assuming compact, complex symplectic manifold, complex symplectic manifold, then you take omega c and its conjugate, and you take their wedge product and any power of them, okay? So omega c to some power k, wedge omega bar c to the power m. Then these forms, as you in fact can expect, they will give you non-trivial cohomology classes in all the cohomology groups that essentially you can define on a complex manifold, okay? Of course, in the rank cohomology of total degree 2 times k plus m, but then also in the Dolbeau cohomology, in its conjugate, in the Bochern cohomology and the Epley cohomology, okay? So essentially, if you have a complex symplectic manifold, the dimensions of all these cohomology groups in, let's say, b degree 2k to m is at least 1, okay? You always have a non-trivial representative in a cohomology class, okay? So they are at least 1. So in fact, when you have, so one can use this result when you have a complex manifold of even complex dimension you can sometimes rule out examples saying, okay, you cannot have a complex symplectic structure because you just look at the cohomology, okay, the dimension of the cohomology groups. But in fact, it follows from this result that we actually have also a topological obstruction. Because if you have a compact complex symplectic manifold, let's say, I mean, this is just a dual, so just take k from 1 to n. If you take the Betti number, degree 2k, this is greater or equal to k plus 1. And this follows from the previous results, okay? So, because what we are saying is that this, the rank these classes, okay, so you take omega k, wedge omega bar m, this form gives non-trivial de Rham cohomology class, okay? So this is closed, and by the previous result, that is essentially, it follows essentially from a Stokes argument, okay? So this is a non-trivial class where in to L, where L is just the sum of k plus m. Okay, so these cohomology classes are non-trivial, but I didn't say this before, but on every complex manifold, there is a natural map that is induced by the identity that relates the de Rham cohomology to the Epley cohomology. Okay, so you have a map from H to L de Rham to this direct sum of H to K to M of Epley, okay? And these cohomology classes are all non-trivial in Epley, so this means that they are linearly independent in the de Rham cohomology, okay? So that's why you have this inequality on the Betti numbers. For instance, I don't know, essentially what we are saying is that, I don't know, before, so the Betti number 4, before, you have, as non-trivial representative, you have omega square, omega wedge omega bar, and omega bar square. So it is at least 3, and so on. Okay, so this is essentially what we are saying. Okay, so we have some cohomological abstractions, and in fact, the cohomology of complex symplectic structure plays an important role in what I'm going to talk about, that are the small deformations of complex symplectic structures, okay? So that's, let's say, the main part of the talk I want to talk about, and we will see that how these complex homologies appear. Okay, so what is the problem here? So it is a natural problem in complex geometry to understand whether, I don't know, if we have a nice property on our compact complex manifold, we want to understand whether this property is preserved is if we deform a little bit the complex structure, okay? So I will not recall, of course, the theory of deformations. So let me just say this. So small deformations of the complex structure, small deformations can be thought in this way. So you can think of M fixed. So the smooth manifold M is fixed, and we are just deforming the complex structure J with a parameter T. Okay, and this T, I don't know, can be in a disk around the origin in C, for instance, or it can be maybe, if we talk about smooth deformations, can be, I don't know, a line, okay? Anyway, so the differentiable structure is fixed, but the complex structure is varying. And if we denote with P a property related to compact complex manifolds, for instance, this property could be the dimension of some cohomology group, or it could be the existence of, I don't know, a nice Hermitian metric, or it could be the existence of a complex symplectic structure, or some other nice geometric structure. So this is the property, and we say that this property is stable if for any small deformations of your manifold. So you start with your compact complex manifold that has this property, and then you deform. For any deformation, you want this property to hold, okay, in the deformed complex manifold. So in this case, we say that the property is stable, or that the property is open under small deformations. Okay, and so, and this is like a general problem in complex geometry to understand whether nice properties of complex manifolds are stable under small deformations, right? So, for instance, of course, the Betti numbers are stable because the Betti numbers do not depend on the complex structure; they just depend on our manifold. The smooth manifold, I mean, it's their topological, but the smooth manifold is fixed, so you are not changing the Betti numbers, okay, if you deform the complex structures. But on the other side, if you consider the dimensions of the Dolbeau cohomology groups, or the dimension of the Bochern cohomology groups, or the Eppli cohomology groups, they vary along small deformations. Okay, the Hodge numbers are the dimensions of, for instance, of the Dolbeau cohomology groups, but same goes for Bochern or Eppli cohomology groups. Okay, they change along deformation. On the other side, a very important result of Kodar and Spencer is that the existence of a Kähler metric is stable under small deformations of the complex structure. Okay, so this means that if you start with a compact complex manifold admitting a Kähler metric and you deform the complex structure, then you still have a Kähler metric, okay? And on the other side, the existence of other Hermitian metrics is not stable. The existence, for instance, of balanced metrics or pluriclosed metrics is not stable under small deformations of the complex structure, okay? And these are, I will not talk about this, but they are some very well-known, well-studied special Hermitian metrics on complex manifolds, and it is known that they are not stable. So what we did with Bazzoni, Freibert, and Latorre was to understand whether the existence of this complex symplectic structure was preserved along deformations. So first of all, what we proved is that the existence of complex symplectic structure is not stable along small deformations. And so this means that, I mean, we will see immediately why, the proof of this, but so I mean that I can start with a compact complex manifold, with a complex symplectic structure, and then if we deform the complex structure, it is not always true that this deformation will admit, again, a complex symplectic structure, okay? And I should say that probably this result was already known to experts, but we were not able to find in the literature any statement of this fact and any proof of this fact. So probably it was known, but we couldn't find any paper stating this result. So we had to come up with an explicit example showing that this property is not stable under small deformations. So one of the many examples we constructed is the following, and it is an Nil manifold. Okay, so we have an 8-dimensional Nil manifold. So let's say G over gamma with a complex structure, invariant complex structure J0. So this complex structure comes from a left invariant complex structure on G. So it comes from a complex structure on the Lie algebra of G. And it has, so we can define this complex structure by saying that we have a global coframe of 1, 0 forms. So Phi1, Phi2, Phi3, Phi4 are 1, 0 forms. So 1 forms, complex valued 1 forms of B degree 1, 0 with respect to the complex structure J0. And the structure equation, the complex structure equations are saying that Phi1 and Phi2 are closed. The differential of Phi3 is the wedge product of Phi1 wedge Phi1 bar. So this notation just means that this is the wedge product of Phi1 wedge Phi1 bar. And the differential of Phi4 is Phi1 2, which means that it's the wedge product of Phi1 wedge Phi2, okay? So you can explicitly write down this omega and show that, so this is a 2-0 form because you only have, you see terms of 1, 2, 1, 3, 1, 4, 2, 4. So this is a 2-0 form. And you can check by the structure equation that this is closed and non-degenerate if B and D are non-zero. Okay, so this is a complex symplectic manifold. So for instance, this is an explicit example of an 8-dimensional Nil manifold with a complex symplectic structure. And then we consider this deformation. So we deform the complex structure by this small parameter T in this way. So Phi1, Phi3, and Phi4 are not changing, but then we deform Phi2 in this way along Phi2 bar. So then you can write down, I mean, it's a direct computation to show that now for this new manifold, this is a new complex structure, so these are the 1-0 forms for these complex structures. And the complex structure equations become this. So essentially, the only term that is appearing, the new term that is appearing is this one. Because of course, if T is equal 0, you don't have this term, and then you find the initial complex structure, okay? So the central fiber of the deformation, okay? But if T is non-zero, you have this extra term. And so we wanted to show that this manifold, these complex manifolds, do not admit any complex symplectic structure, okay? Any complex symplectic form. So how do we do this? So it's, we do like this. So you take an invariant 2-0 form. So an arbitrary invariant 2-0 form can be written in this way. So you have all the 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, okay? So this is the generic invariant 2-0 form on the manifold with complex constant coefficients, okay? So we want to understand, I mean, we want to find a contradiction. We want to show that omega c cannot be complex symplectic. So we impose closeness. So we compute the differential of omega, and we pose that this is closed. It's a direct computation. And what you get is that zeta has to be 0, tau has to be 0, and t theta has to be 0. Okay, so they vanish, of course. So what happens is that if t is non-zero, so we are not in the central fiber, then theta has to be 0. But now we have the tau, zeta, and theta are 0 that are here. And so what happens is that omega to be closed has to have only these 3 terms, but so it cannot be non-degenerate. So omega squared is 0. And so this proves that we cannot have, we don't have any invariant complex symplectic form on the deformation. But this is not enough, of course, because I'm just saying that we cannot have an invariant complex symplectic form, but we could have a non-invariant complex symplectic form. So for this, what helps is this result by Bazzoni, Freiberg, Latorre, and Menke, that say essentially this is saying that we have a symmetrization process, okay? But we have some assumption. So if you have a solved manifold, so in particular in our case we have an in manifold, such that the Duran cohomology of the solved manifold can be computed using only invariant forms. Essentially, this is the Chevalier-Eilenberg complex cohomology of the algebra. And we have J that is an invariant complex structure. Then the proposition is saying that if our complex manifold admits a complex symplectic form omega, not necessarily invariant, then there is an invariant complex symplectic form, okay? So how do we apply this, this proposition? As follows, because we have an in manifold, so by Nomizu's theorem, we know that for in our example, the Duran cohomology can be computed using invariant forms. But then we can apply the proposition. So this means that our complex deformations do not admit complex symplectic structures for any t different from 0. Okay? Because if we had a complex symplectic structure for t different from 0, then we apply the proposition, we would get an invariant one, but by what we showed here, we cannot have an invariant complex symplectic form, okay? Okay, so this example is showing that we don't have stability in general, okay? But in the literature, there were some results saying that under some suitable assumption, we can have stability, in fact. And in fact, we have examples where we have that the deformations still admit complex symplectic structures, okay? For instance,
Nicoletta?
Yes, please.
May I ask you something?
Of course.
In the example, did the Hodge numbers, I don't know, 1, 1, 2, 0, change with the deformation? Do you know?
I didn't, let me think, because for sure we didn't check the Hodge numbers, but I think we checked the H20 Bochern, because you will see later that in fact if H20 Bochern is not changing along the deformation, then we have stability.
Yes.
Okay, so indeed, I mean, the cohomology is saying can help in understanding whether we have stability or not. But no, I did not compute the cohomology of this deformation. For instance, the Hodge numbers.
So there could be a cohomological proof for this, that
we cannot have in the deformation. Could
yes.
Be. Yes.
Maybe the 2, 2 is the one, it has to be positive as a necessary condition?
Yes.
Maybe. So, okay, maybe 2, 2 is 0 here, but we don't know.
Yeah, no, I don't know. Okay. We could check. No, I don't know. We didn't check this. Thank you. No.
Thanks.
Yeah. No, you're right. Maybe I didn't check that. And yeah, so again, so we have these examples where we don't have stability, but we can have stability along in other direction. For instance, you can take the Iwasawa manifold. That is, well, this is a three-dimensional manifold, okay? And phi1, phi2 are closed, and the differential of phi3 satisfies this equation, so it's equal to phi1, 2. And this is, again, an manifold. And the small deformation of the Iwasawa manifolds are very well known. They have been studied first by Nakamura. And so the deformation space is, let's say, given by these 6 parameters. And Nakamura, in his paper that was done, I mean, let's say, improved by later, many years later, by Angella, but in his paper divides the deformations using Hodge numbers in 3 classes. And well, I will not go into the details because I don't need this, but the idea is that we took one of the, these deformations of the Iwasawa manifold times a torus, okay? And so we consider this product, okay? So this is a 4-dimensional manifold. And it turns out that for t equals 0, we have a complex symplectic structure. It is very easy to construct. So we take these deformations, and it turns out it is a direct computation that, in fact, we have direction where the existence of complex symplectic structure is not preserved, but we have other direction where the existence of complex symplectic structure is preserved. So we wanted to understand how can we detect these directions, essentially, okay? Because in fact, as I was mentioning, there were already some results saying that the existence of complex symplectic structure is preserved along small deformations. For instance, if the deformations satisfy the Didi-Bar lemma. So you can just look at this condition, okay? So the Didi-Bar lemma means that all the cohomology groups we saw before are naturally isomorphic, okay? So all the cohomology groups are isomorphic through the identity maps, essentially. So if your manifold satisfies this property, Antes, Cattaneo, Orlensky, Tomassini proved that the existence of complex symplectic structure is preserved. But we cannot use this theorem to explain, for instance, the behavior we have on the Iwasawa manifold times the torus, because that is an manifold, so it cannot satisfy the Didi-Bar lemma, okay? So this condition is not satisfied by the previous example, this Didi-Bar lemma, okay? So we looked for other sufficient condition ensuring stability. So, for instance, what we proved is that if we start with a compact complex symplectic manifold and we consider a smooth family of deformations, if we assume that the dimension of the Bochern cohomology group of B degree 20 is constant along the deformation, then the deformation still admits a complex symplectic structure, okay? These numbers, so as I said, the Bochern cohomology is finite dimensional, but along deformations, this number can change. It was proven by Schweitzer that these maps are, in general, upper semi-continuous, okay? So the dimension of the Bochern cohomology can drop along the deformation. But if it remains constant along some direction, then along that direction, the complex symplectic structure is preserved, okay? And we have examples of manifolds satisfying that where we can apply this result. For instance, again, if we take the 8-dimensional manifold we saw before, this is the same manifold we saw a few slides before, and we take another deformation, now we change phi1, okay? We perturb only phi1, the first form. Then the complex structure equation becomes like this. So we have these extra terms again. But the point is that H20 is not changing along the deformation. You can compute direct, I mean, there are some theorems that ensures that you can compute directly, easily, the Bochern cohomology of these complex manifolds along the deformation. And the dimension of this space is not changing. It is 4, it is equal to 4 for any t, okay? And so we can apply the previous theorem, and we know that the deformation has a complex symplectic structure. You can write it down explicitly. For instance, you can show that this is a complex symplectic structure, but already the theorem is saying that we will have stability. Another sufficient condition ensuring stability comes from other cohomology groups, not the Bochern cohomology, but some subspaces of the de Rham cohomology. So, for instance, if you have, well, assuming it's a complex manifold, okay? It's more general than that, but assume it's a complex manifold. Then Angela and Tomassini, inspired by a paper by Li and Zhang, constructed these subspaces of the de Rham cohomology in total degree P plus Q. So they define this HPQ. And it turns out that there exists alpha, that these spaces are defined that you have a class A such that there exists a representative alpha for this class of pure B degree, PQ. So these are these cohomology groups, okay? Classes in total degree P plus Q with a pure degree representative. And a complex structure is said to be complex infinity pure at the K stage if the intersection of these spaces as in total degree K is trivial, because in general it's not trivial. And it is called, Jade's called complex infinity full at the K stage if the sum of these spaces in total degree K gives the full de Rham cohomology in degree K. The de Rham cohomology group in degree K, okay? And if both conditions are satisfied, then we have a direct sum decomposition, and then so we say that J is complex infinity pure and full. And so now assume that we have a compact complex manifold that is complex infinity full at the second stage.
Nicoletta,
yes.
Sorry, are you asking for the intersection of all of them, or
yeah, no, all of them
with the sum of the others? Because otherwise, I don't understand why do you get direct sum with only this condition?
Because of the B degree. No.
But you have
because
this
if you have I mean, the definition in K stage, yeah, it's this one. Yeah. It's this, not just
linearly
independent. Yes, I think you get linearly independent probably. You probably, maybe it's a line you have to prove this, but yeah.
Okay.
Yeah. I mean, it's the whole intersection on P plus Q equal K. Okay.
Thanks.
Okay, thanks. But what I need is, in fact, this condition at the second stage, because, I mean, I'm working with a complex symplectic form, so essentially every condition we put can be put essentially on degree 2, because that's the form we want to preserve along the deformation. So assume that we have complex infinity full at the second stage. So, and suppose that we have this form, okay, omega, that gives a representative in the de Rham cohomology. But now we can decompose the de Rham cohomology with these spaces, H20, 1, 1, 0, 2, which means that if I have a closed form, omega, complex valued closed form, okay, 2 form, then omega can be split as a sum of a 2-0 form plus 1-1 form plus 0-2 form, which are the representative in the 3 classes. And this is the infinity full at the second stage. But since we have this representative in the de Rham cohomology, then this is equal up to an exact form. Okay, so this d gamma is a differential of a 1 form. Okay. So we have this condition, and so this idea was first introduced by Latorre and Ugarte. So the idea of introducing this space that helps in the deformation. So delta x omega is defined as the space of 1 forms, complex valued 1 forms, whose differential of gamma, so the differential of this 1 form, is equal to omega minus these alpha 20, 1, 1, 0, 2, these are some closed forms. Okay. So if we want a complex infinity full manifold at the second stage, so this space is non-empty. But now, so the important part here is that we are going to deform the complex structure. So the B degree of the forms is changing along the complex structure, right? So for instance, if I start with a complex symplectic form that has B degree to 0, and I deform the complex structure, my starting complex symplectic form will not be of B degree 2, 0 along the deformation. Okay, so these alpha PQ depend on the bigradient induced by J, and also the differential del and del bar are changing with the complex structure, okay? So there are many things that are changing. However, one can prove that if we have a compact complex manifold with a complex symplectic form, and suppose that we have so this differentiable family of deformations, so assume that now along the deformation xt is complex infinity full at the second stage, and there is some gamma t in this space, delta xt omega c, that satisfies the condition, this condition. So this gamma t is a one form. So we want that its component in B degree 1, 0 for JT has to be DD bar closed. So if we have this, then the deformation is complex symplectic. Essentially because our omega, so the form, the complex symplectic form, if we change the complex structure, so with respect to JT, this is not of type 2, 0. It will have a component of type 2, 0, a component of type 1, 1, and a component of type 0, 2. All right? So essentially, we want our omega also with respect to this decomposition, it will have a component of type 2, 0, 1, 1, 0, 2 plus the gamma. But the importance of this decomposition is that now alpha 2, 0 is closed with respect to the complex structure JT, okay? So that's the important part, because our omega c was closed at the beginning, but it was of B degree 2, 0 at the beginning, but along the deformation is not of B degree 2, 0, and its 2, 0 component is not closed. But now this is, using this decomposition, this is closed, but you also have this extra term, the gamma. So actually it's the del of gamma that will give some part in the 2, 0 component of our symplectic form. Okay, and you want that to be DD bar closed to ensure that the complex symplectic form along the deformation is closed, essentially.
So
okay.
Nicoletta,
Yes.
so the 2, 0 component is still a complex symplectic form for any T. That's what you're saying?
Well, the 2, 0 component plus, yes, but you have also this other part. You have this del bar part. I mean, you added something else. Well, the 2, okay, so sorry. In the end, the 2, 0 component will be closed.
Yes, but
what ensures closure is this condition.
I see. But what about non-degenerate?
Oh, yeah, for T small, it's okay.
Yeah, but the component 2, 0 is not necessarily non-degenerate, right? At the beginning or I mean...
No, I mean, no, yeah, you can check that. I mean, you have to prove that. As I was saying, I mean, this is not okay. No, I mean, you're right. You have to check also that, but that is okay. Okay.
Okay.
Okay, no, thank you. Yeah. You're right. You're right. Yes. And we have examples of manifolds satisfying this condition. I mean, we were able to find examples satisfying all this sufficient condition. And so how much time do I have?
Um, 5 minutes.
Okay, so probably, okay, I will skip this. I mean, this is an example where this condition, for instance, is satisfied. We have a complex infinity full at the second stage, and so on. So what I wanted to show is probably this, that in fact we have examples that do not satisfy the sufficient conditions for the stability, okay? And so the problem is that sometimes, as I was saying, we find like deformations where we have stability, but we don't know why, okay? Because we were wondering, okay, are there conditions that are ensuring this stability along these deformations, okay? So for instance, if we take this example, so it's an 8-dimensional manifold. Again, it's the torus times Iwasawa, okay? So with this basis, so the structure equations are this, and omega is a complex symplectic structure, okay, on the manifold. This omega is phi 13 to 4, okay? So this is non-degenerate of B degree 2, 0, and it is closed, okay? Because 1 and 3 are closed, and phi 2 is closed, and the differential of phi 4 involves phi 2, okay? So this is a complex symplectic structure. And we considered this deformation, this small deformation. So here we wrote down directly the complex structure equations, okay, for the deformations. And it turns out that, again, we have a complex symplectic form along this deformation. So this omega t, again, is complex symplectic, okay? But the sufficient conditions of our results are not satisfied, because you can compute the Bochern cohomology. In particular, for t equals 0, you compute explicitly H20 Bochern, and it has dimension 5. But for t different from 0, H20 Bochern has dimension 4. So as I said, the dimension of the Bochern cohomology is an upper semi-continuous function depending on t. Okay, and so in this case, in this particular example, the dimension is dropping, okay, from 5 to 4. So this function is non-constant. So the sufficient condition we saw before was not satisfied. Moreover, you can show that this 2 form now, phi 3, 4 minus t, a is a constant, take a equal 1, okay? Phi 1 bar 4, this is declosed. Okay, so this means that the complex structure for t different from 0 is not complex infinity full at the second step, because we have this form that is of non-pure type. Okay, so we have this deformation that maintains complex symplectic structures, but it is not satisfying so our sufficient conditions. So how could we detect this deformation? So this is part of a work in progress. I mean, it is very, very in progress. I mean, we are very far from being done. But it is a work in progress with Tomassini. So we, again, were trying to understand these complex symplectic deformations. And now the idea is to deform, instead of the complex structure, we started deforming the, we started deforming not the complex structure, but the symplectic structure, okay? So here, the idea is we constructed this deformation. Instead of deforming really IT, we deformed omega as follows. So this is the idea, but again, it's a work in progress. There are probably some details to be fixed. But the idea is that, okay, so denote with Zi the vector fields that are dual to the 1-0 forms phi. And we consider the distribution generated by Z1, Z4. And we consider a 1-1 form, eta. So this is a Lagrangian distribution. Okay, so omega here is vanishing. And we define eta as essentially it's a 1-1 form defined starting from these vectors, okay? And it is closed. So this eta is closed, okay? Phi 1 was closed. And omega, we deform omega in this way. We take omega t to be the starting complex symplectic form omega plus t eta, where t again is a complex number, okay? And in this way, well, if you do the computation, you see immediately that this is the form you get. And it turns out that this form is C-symplectic, according to the definition of Verbitsky. And you can show this explicitly. It is closed because omega was closed. It was a complex symplectic form, and eta, again, it is also taken to be closed. Then you take omega to the power n plus 1, so omega to the power 3, and this is 0. It is, again, direct computation to show that it is 0. And the final condition for the definition of C-symplectic was that omega square wedge omega bar square is non-vanishing, okay? And you do the computation, and it turns out that omega t square wedge omega bar t square is equal to omega square wedge omega bar square, okay? So this is non-zero. So what does it mean? It means that this omega t is a C-symplectic form, and so by Verbitsky, omega t is defining an integrable complex structure IT with a coframe of 1-0 forms that you can write down, okay? Because if you remember, the 0-1 the 0-1 vectors were given by the kernel of omega, and then you can construct what is the complex structure, and it turns out that the coframe of 1-0 forms is given by this. So then you get the complex structure equation, and then you get the deformation that is a complex symplectic deformation. Okay, so the deformation that we constructed before that was not satisfying any of our sufficient condition has been constructed in this way, where essentially we deformed omega in order to have a C-symplectic form, and then we recover the deformation for the complex structure something from them. And so, again, this is suggesting this result, but this is a work in progress. But the idea would be the following. So to have, for instance, just like in the examples, you have a compact quotient of a Lie group by a lattice. We take an invariant complex symplectic structure on the manifold, and we take a Lagrangian distribution generated by this linearly independent invariant vector field, say Z1, Zn. And we take eta, that is essentially the form that is deforming, to be defined on this distribution as a 2-0 form plus a 1-1 form. In the example, it was a 1-1 form, but it's not a problem if you add a 2-0 part. That is declosed. And then omega t turns out to be a C-symplectic structures, where omega t, just like in the example, is defined to be omega plus theta. Okay, and this becomes a C-symplectic form. Okay. As a consequence, once we have this, we have a complex symplectic structure, because if omega t is symplectic, now we can apply the result of Verbitsky, and this defines an invariant complex structure IT such that M IT omega t is a complex symplectic manifold for every t. Okay. But as you see, so it's a different point of view. Essentially, to detect these good deformations, we are not really starting from the complex structure, okay? We are starting from the complex symplectic, we are starting from the symplectic form. We are deforming the symplectic form in a good way so that we bring with us also a deformation of the complex structure. But again, this is a work in progress with Tomassini. And yeah, sorry. I can stop here. Thank you.
Okay, thank you very much, Nicoletta.
Thank you. I'm a bit late. I'm sorry.
Okay, so are there questions, comments?
Yes. In manifold with one of these structures, could it be that the complex structure is not nilpotent? Are they always nilpotent?
Okay, I think they were trying to construct something with like a strongly non-nilpotent complex structure, but they couldn't find any example. I think it can be non-nilpotent, but I don't have in mind an explicit example, actually, now.
Okay.
You're right. Probably the reference good to look at is the paper by Bazzoni, Freiberg-Latore, and Menke, where they study these nil manifolds admitting complex symplectic structure, and then they study this reduction, oxidation, and then they also discuss when they have quasi-nilpotent complex structure and strongly non-nilpotent complex structures and so on. And now I don't remember if there is an example, so I'm sorry. Yeah.
Okay, thank you.
Thank you.
Okay, I had another one. So, which theorems are those which you use to compute the Bochern cohomology of the animal?
The one by Angela and Kazuya. I mean, because essentially when you have manifolds where you know that you can compute the Bochern cohomology, the Dolbeault cohomology in an invariant way and the round cohomology in an invariant way, then you can also compute the Bochern cohomology in an invariant way. This was, in fact, proved more general also by Stelzik. So it's a combination of these results.
Okay, but you need to compute the Dolbeault cohomology in the.
You need to know, well, you need to know, if you know that the Dolbeault cohomology can be computed for some reasons, for maybe some other theorem, some other results, you know that the Dolbeault cohomology can be computed using invariant forms, then you can also compute the Bochern cohomology using invariant forms. Yeah.
Okay.
Yeah, otherwise, of course it's not. Otherwise, no.
One question. Is there a natural flow for complex symplectic structures?
I don't know. No, I'm not. I don't think in the literature I saw any natural flow. No, I don't know. Because, I mean, there are not many non-Kähler papers about complex symplectic structures, actually. Or holomorphic symplectic, because sometimes they are called also holomorphic symplectic. Which can be misleading because also irreducible holomorphic symplectics are hyperkähler, so it can be a little bit misleading, but yeah. There are not many non-Kähler results, so yeah.
Many thanks. Nice talk.
Thank you.
Are there questions? No? Okay, so let's thank Nicoletta again.
Okay. Finally, I see you.
Yes.
Yeah.
Okay. So.
Okay. So thank you.